So let's go ahead and take a look at a few examples. So let's say we have this problem right here. So we could have something like the sine of x, um, plus 2xy minus 3y equals 4. Okay, so notice in here we have x's and y's, but remember I said something earlier. I said that we have to be careful about what rules we're using. When we have our derivative rules, all those things still could come into place. Means we could still have to use a product rule or a quotient rule or a chain rule, along with knowing how the derivative of sines behave and other types of functions that we could have in here as well. So I'll just point out one thing for you. Notice that in the middle here, there is a 2 times xy, okay? There's a product there. We are going to have to use a product rule in this problem. And again, you're not going to be told in problems, you have to use a product rule here, but it's good to be able to identify, is there anywhere where you have a variable multiplied by another variable or a function multiplied by another function? Not just a constant, but do you have variables being multiplied together? So let's start here on the left side. What we're going to do is we are going to take the derivative of both sides, just like we did before. So I'll go ahead and put d over dx of both sides over here, and d over dx of 4. Okay, which I guess we could start over there. We know that's going to be 0. Okay, let me actually, I don't know how much space I'm going to need here, so let me give myself a little bit more just in case. So equals 0 on the right side, because the derivative of a constant is always 0. Now go term by term. The derivative of a sine is a cosine, and we want to really be careful about, do we have an x or do we have a y inside? Because if we had a y inside, then that would be a chain rule, and we would need a dy dx in that part. As it is, this is just the sine of x, so the derivative of sine of x is just a cosine of x. Okay, now I'm going to put the minus 3y, let's deal with that next. We'll deal with that product rule at the very end. So the derivative of minus 3y, remember, it's kind of like minus 3 y of x here, where you have this minus 3 just kind of tagging along out front. That's a constant multiple, or constant multiplier, and then you can take the derivative of y, but remember it's dy over dx. It's not just, oh, there's a y, treat it like an x, you just get an answer of 1. No, you don't. You get a dy dx, and you get something different on top and bottom, so you got to leave that in there. So you get minus 3 dy dx for that last piece. Okay, if that y had a different function on it, like a y squared or something else that was a little more complicated, we would need to take the derivative of whatever else was there that's more complicated and then multiply by dy dx on the end. Okay, so now what about that product rule? I'm going to go ahead and put parentheses here just to recognize, hey, there's a product rule here. We got to be careful. You can handle this in a couple of different ways. You can either leave the 2 out in front and deal with x times y as the product, or you can think of this as 2x times y, where 2x is your first term and y is your second term. Either way, it's up to you. You should get to the same place. Just be careful. If you're going to leave the 2 out front and then just deal with an x and a y separately with a product rule, then you need to put a 2 outside of the parentheses and then the product rule inside of the parentheses. I think for me, I prefer to do 2x as my first term and y as my second term, but you can take your pick of what you prefer. Okay, so the derivative of the first term right here is 2. And then the second term, remember the product rule says the derivative of the first times the second plus the first times the derivative of the second. So here's your 4 pieces of your product rule. So derivative of the first times the second plus the first, so copy and paste to 2x, times the derivative of the second. Now the derivative of the second is the derivative of y. You need a dy dx. Keep in mind when we said the derivative of the first times the second, it was just copy and paste the second one. It didn't say times the derivative of y. It just said 2 times y, or the derivative of the first times the second. Just copy and paste, rewrite the second function that's there. So you don't need a y prime or a dy dx in both of these pieces, but you do need a dy dx anytime you take the derivative of something that has a y in it. Okay, that's just a good rule of thumb in general for any kind of a function, for any kind of a problem here. Anytime you take the derivative of something that has a y in it, You need a dy dx in there somewhere. It doesn't mean just throw it on the end. You got to be careful about where it goes with your derivative rules, but you need to have a dy dx in there somewhere when you're taking the derivative of something with a y in it. Okay. All right, now, if my directions were the same as the last problem, where I want to say something like find dy dx, in other words, get dy dx by itself, we got to think about how I could do that. That's going to involve a little bit more algebra. So I have a dy dx here and a dy dx there. I actually have a dy dx in two different places. Let's move everything else over to the other side. I will point out that these parentheses just help me recognize that there was a product rule, but they're actually not needed as far as algebra steps or as far as simplifying goes, because it's all it's all addition in there. So the cosine of x and the 2y that do not have a dy dx in them, go ahead and throw those over to the other side. Okay, so it's going to look like this: 2x times dy dx minus 3 times dy dx equals negative cosine of x minus 2y. Okay. And anytime we have a problem where we have something show up in two different places and we want to solve for it and get it in one place, it's kind of like if we had something like 4x plus 7x, how do we get just x's by itself? You'd combine those and say that's 11x. What you're really doing there, though, is you're factoring out an x, and then you're adding 4 plus 7 together. And same idea here is let's factor out a dy dx. Okay, so factor out a dy dx, so that way we only have it in one spot. And then we have 2x minus 3 left over on the inside equals negative cosine of x minus 2y. And now to solve for dy dx, get dy dx all by itself, we can go ahead and divide by 2x minus 3, okay, because they're being multiplied right here, and move that over to the other side, get dy dx all by itself. So we're going to end up with an answer like negative cosine of x minus 2y over 2x minus 3. Okay. Now, what on earth are we finding here? Okay. Here's the pretty cool thing about this. I don't know what the original function looks like. I do know that it's pretty complicated. It has a sine function in it. It has not just an x and a y, but it actually has an x times y, which is going to make things pretty complicated, plus an additional term that has a y in it as well. This is not going to be a very friendly function, or it's not even going to necessarily be a function. It's not even a very friendly graph. So what you could do, though, is if you could find a point on that graph, an x and a y coordinate, and you want to know the slope of the tangent line at that specific point on the graph, you just need to know its x coordinate and its y coordinate. You can plug in the x coordinate and the y coordinate here on the right side, simplify and get one number, and that will give you the slope of the tangent line at exactly that xy point on that graph. And that's true regardless of how complicated that graph is. It's true regardless of how complicated the point is that you find. Okay, you got to go find the point first so that you know what to plug in for x and for y, but you can find the slope of that tangent line by just plugging that in, plugging those values into this equation once you've solved for dy dx. All right, let's go ahead and take a look at one last example here, because again, I think this takes a lot of practice. And for this example, I'm not actually going to graph this because it's way complicated, but what I would recommend is that you go grab a graphing calculator, or maybe not even a calculator. If you have some kind of computer software, I recommend using a website if you want to check out some crazy looking graphs. It's www.desmos.com. Some of you know about this already. This is a great website for you to be able to just to graph some crazy things, and you don't have to have them in y equals form in order to graph them. So my recommendation, just to check out what this looks like, is to go to Desmos and to try to graph this. Just type it in as the original equation shows you, and you'll see the kind of equation or the kind of graph that we're talking about here. This gets really pretty crazy. So the sine of xy, which that already in itself is crazy enough, is equal to the sine of x, okay, plus the sine of y. Okay, so I'd recommend you go check this out on Desmos. And our goal here is going to be the same. Can we find dy dx? Okay, so pretty clearly, if you were to go take a look at this graph, you'd say, wow, we took a step up from just being able to take a quadratic or a polynomial or a root and have y equals and then go find the derivative. This graph is much more complicated, much more interesting, okay? But the same rules apply. We just got to be careful with our derivative rules. So d over dx of the sine of xy, which, by the way, I'm pointing out some of these rules, but I hope that you're seeing these along the way. When you see sine of xy, do you see both a chain rule and a product rule? In other words, there's a product rule xy inside of a function sine. So there's you can deal with the derivative of the outside function, the sine, and then when you talk about the derivative of the inside function, then you're going to have a product rule in that derivative. Okay, so d over dx of the left side, d over dx of the right side, which is sine of x plus sine of y. And go ahead and follow along with me. Again, there's a chain rule here. Take the derivative of the outside function. Hopefully we're getting faster with these chain rules now that we've seen them a little bit. Take the derivative of a sine, you get a cosine. What goes in the parentheses when you take the derivative? Well, it was just whatever was in the parentheses at the beginning, whatever the input was. But then you need to multiply by the derivative of the inside. The derivative of the inside is x times y. That's a product rule. Within that product rule, you take the derivative of the first, which is 1, times the second, plus the first times the derivative of the second, and that's where your dy dx comes in. Okay, on the right side, the derivative of a sine of x is just a cosine of x, and the derivative of a sine of y is a cosine of y. And this is like a chain rule in here as well. Think about it as like y of x. So there's the derivative of the outside function. With the chain rule, this is like your f prime of g part. But then you need to multiply by the derivative of the inside, which is dy dx. Okay, so pretty complicated, but that's how we can take the derivative of every piece separately. Now it's just some algebra, get dy dx all by itself. Okay, take this cosine of xy and distribute into the parentheses. That looks like y times cosine of xy plus x times cosine of xy times dy dx equals the cosine of x plus cosine of y dy dx. Okay, so you want to combine the dy dx's together. You want to get those two on the same side, and you want to move everything else that doesn't have a dy dx in it to the other side. It's kind of up to you which way you want to move things. I like to try, if possible, if it doesn't give me too many negative values, I like to try to throw my dy dx's over to the left. And so it's going to look like x times the cosine of xy times dy dx minus the cosine of y dy dx. So I'm moving the cosine of y times dy dx over to the left side, and then we're going to move this y cosine of xy over to the right side. So it's going to become cosine of x minus y times the cosine of xy. Okay, now I'm running out of room, but now go ahead and factor out a dy dx and divide everything, divide both sides by what's left over after you factor out that dy dx. So that's going to look like dy dx, and then in the parentheses, going to be left with, I think it was an x cosine of xy, and then minus cosine of y. And then this is all supposed to be equal to, just double checking over here, cosine of x minus y times the cosine of, now dy dx all by itself is equal to cosine of x minus y cosine of xy, all divided by x cosine of xy minus cosine of y. A lot of cosines in there. I actually don't really see anything that you can simplify here, even with all the cosines and the x's and the y's. I think that's going to be pretty good. So not much we can do there to simplify. Okay, so this is going to be it for examples. I hope this makes sense, or at least makes sense with some practice. I hope you've enjoyed the video. Good luck practicing.